Alright, it's working. Oh, it's hard to sit still enough. If I move my body, or if anything comes near it, it'll scare it away. Yeah? Well, what the hell have we here? Well, let's take a look at it. And let's unplug it first. Alright. Let's take a look. Get a little light here. You know those little radar activated detector things they've been selling for $1 or $2? Well, if you modify one to get the analog data out and process that, you can do lots of tricks with it. Here's the little module inside. What we have here is your standard RF motion detector module, RCWL something or other, and with a little built-in antenna here. This part is left off when they sell it. It's the photocell made to disactivate this in the daytime. The unit was made apparently to activate a security light. When it's triggered, it has just a digital output, and that digital output stays on for a number of seconds once it's triggered. So this little blue wire here is part of the two-step modification to take the actual analog signal off of, I think, pin 12 here, 8, 9, 10, 11. Pin 12's got the nice analog signal before they process it, and this nice little blue wire picks it up here and puts it out this spare pin. On the other side there's a trace cut. We cover that in another video here. So basically there's only requires 2 connections into the AT Tiny 85 here. One is the analog signal is fed out and analyzed, and 2, a digital signal is put out, keying a small NPN transistor hooked to a speaker just to make some kind of growly noises. And because it's analog out, we can do it proportional to the signal, which is the whole idea of using the analog instead of the digital output. So now what we're going to do is actually connect this up to our development system. So let me swing back here. Okay, we're hooked in now. And now we got to plug this in. So this is our part of our development system. Standard USB to TTL, hooked to a proto clip with the wires to the right pins to download Arduino. The cable is rigged with the 0.1 microfarad capacitor used to create a reset pulse, and a Schottky diode used to feed power without getting screwed up if power's already there because of the external power feed. You hear a little noise from it now, just from the 5 volt leaking through to the speaker. It's much louder when we plug in the 12 volts. We'll show you that maybe later. So now let's look at the scope here. The top trace is that analog output, and you notice with no motion around it, it's rather steady. And anything that moves, and I mean anything in the room, I've been on the other side of a wood wall from this and still had it pick me up. So especially large objects. And what you see on the bottom trace is the digital pulses it's generating in response to a wiggle in the line there. Okay, so we're going to go now take a look at the software it takes, which isn't much at all, by the way. to do this whole process. Here's the program. This is now running on a 1 megahertz clock. Okay, that just saves some power. This doesn't take a lot of processing power. Set up pin PB3 for output, usual stuff. So what we do is we make an analog reading, and after basically trial and error, to tell you the truth, came up with this averaging formula, and all it does is store in average, which is along, and notice average is defined outside of loop. The trouble with loop is it's not like a regular loop in C. Every time this goes around, all these internal values are reset. So in order to maintain a running average, it's got to be defined outside. And I also made it a long, just to make sure I don't overflow anything. Anyway, you read it, 19 times the average plus the current data divided by 20, so that makes 20 units divided by 20, and this just makes a nice sliding average. That gives us our baseline. Then we just take the current data minus the average, and that's our deviation from the baseline. Take the absolute value, because we just don't like negative numbers, and call it the frequency. Now, we set a minimum up here someplace, okay. So we don't want to make a noise all the time. It's only when frequency's over minimum, then we squawk frequency. Then we delay what amounts to a millisecond. So this loop runs once a millisecond, which seems to be a good time to run, because really the data coming out is a very low frequency, a few hertz at most, so that's plenty fast to run the loop. And then we have our little routine called squawk. Well, what does squawk do? Well, I wanted something that was proportional to the frequency, called F, coming in here. So what we do is we set a bit high, delay microseconds 1000. So we have a 1 millisecond delay, and then set it low. So we create here a 1 millisecond pulse. Now, this routine is your standard way to make a linearly proportional time. If you use the frequency as a down counter, then it's going to be inversely proportional to the frequency. Because we count to a specific value, but I plus equals F, this is our step each time. Notice how tidy it is putting right in the for loop. Then the bigger F is, the faster this is going to go through its count to reach 10,000 with a specific delay of 50 microseconds. And that's it. Now that's all the code, folks. That's it. Okay, read it in, average it, frequency, blah, blah, blah. And so basically if we just plug it in here, the usual plug it in sound, and now we can, well, let's see, we got AT tiny, it's the 85, clock source 1 megahertz internal, okay, running that normally, whatever the hell that is. We enabled the milliseconds, microseconds, because we were using it. Who cares about brownout? We're on count 4. Okay. So now all we got to do is hit the little arrow. Go, baby, go. Okay, uploading. There we go. Alright. Reads it back. It likes the code. Alright, now we're running again. And yes, move my hand around and there it goes. So that's how the code works. Okay, we've got it all reassembled back in the box. Now, one trick I learned here, I was looking for little plastic project boxes, but none of them quite had room to put a speaker in, and then I'd have to find a speaker. Well, one way to do it is to go to your thrift store and buy these little speakers for $1 or $2 a piece. And whatever circuit you want that drives the speaker, just build it inside the speaker box. Makes it all really tidy. So basically, if you haven't figured out what this is about, yeah, well, join the club. It just seemed like a cool thing to do. But I would say if I want to keep my cat off of the sofa or something, I could put this there for a while, and as the cat approached it, the cat would be very annoyed, I'm sure, with a sound like this. An animal should sense that their motion has something to do with the reaction. Now, I could walk clear across the room and you'd still hear this damn thing going. So let me pull the power here. Alright, there we go. Mount a little power jack in the back. Wire it to the speaker inside. Lots of room. Turned out pretty good. Well, that's a wrap for this project, folks. The details on the mods to that little radar board are on another video, as are some more explanation as to the different development setups I use here with various cables, clips, and other hookups. Let's see. Yeah, because what the Arduino is really good at is that download feature. It's got a really nice C compiler and download, and I tell you, I would use this in real commercial applications, because you could walk up to a machine after it's all built and on the factory floor and have yourself a little data jack on the side that nobody else knows about, plug into it with a laptop computer and update their software, rather than taking the machine apart, pulling a chip, reprogramming. So that's why I like the whole Arduino development system. It's really, really a fine engineering tool. So we'll see you next time. Have a nice day.